Welcome, everyone. My name is Greg Risterbin from Olympus NDT. I'd like to welcome everyone today to this installment of our new webinar series entitled Introduction to Phased Array Inspection Using the OmniScan MX2. This series is designed to take the participant through the basics of preparing a single group phased array inspection using the OmniScan MX2. Today's installment is part one of the series and will cover the essential ingredients of phased array and basic theory. Our presenter today is Chris Magruder. With more than 20 years in the inspection business, Chris is the phased array AUT manager for Olympus NDT and has been developing and delivering phased array systems for over 12 years. This webinar is budgeted for about 60 minutes. The main presentation should last approximately 45 or 50 minutes, leaving 10 or 15 for questions. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the course of the presentation. Do not type your questions into the chat panel, as we do not monitor chat for the Q&A reasons. If we don't get to your questions during this live webinar, they will be addressed personally either by email or by phone after the event is over. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, it's all yours.
Good morning, everybody. Again, my name's Chris Magruder. We're very happy to have such a big group with us today. We're going to be taking the users through an MX2 training course that we've been working on over the last year, mostly with the highlights. If you should miss something because of the video or audio, again, you'll receive an email with the video and the follow-up questions and links to the presentation. Most of the information we're going to be talking about can be found in much greater detail in the references you see here that are available on our website in PDF format, free of charge. Most of what we're going to be learning are practical examples and a working man's version of conventional UT transitioning to a single group phased array instrument. We're going to be talking today about some of the hardware and software used to develop the phased array, and we divide these into 4 specific groups. 3 parts hardware: the probe, the wedge, the material, and 1 part software, the focal law. There's going to be 4 environments we're going to be using throughout the training where you'll be able to see on my desktop. And sometimes it takes a few seconds to transition between the desktop and the presentation, so bear with us. The first of the environments is OmniPC. This is the offline viewer we use to look at data files acquired from one of the OmniScan family of instruments. We wanted to talk a little bit about some basics and review prior to moving on to the phased array. And the first point I'd like to make is that an A-scan is an A-scan. The A-scan you're seeing here was generated with a phased array probe, a focal law calculator, and the associated instrumentation. It's linear, it's repeatable, the time base can be calibrated, the amplitude and TCG can be calibrated. So in regards to this being a new technology, that's true, but in fact, we're using all the old rules of physics. So our ability to comply with conventional procedures and existing qualifications is often fairly easily repeatable. So we can see right away from one single phased array probe, like we're seeing here, looking at a regular calibration block, we can change the angle, the beam shape, the focal point, and many parameters of this A-scan that were previously related to hardware. Instead of looking at 20 of these A-scan windows or 100 of the A-scan windows, a sector scan type of display is used that's mostly associated with the phased array. This view is simply a way of looking at many A scans simultaneously. All the information here is available here. And from the one-line scans that we'll be programming and learning to manipulate, like you see from a simple beam plotter here, it greatly simplifies the inspection and allows us to encode it so that with fairly simple mechanics, we can see C scan, B scan, D scan type side views with a much simpler system than we used previously. But the point I'd like to emphasize is that an A scan is still an A scan and can be calibrated in the exact same way. It's simply a matter of managing data and managing more of them and the tools we use to do that. So back to the presentation. In today's lesson, we're going to mainly focus on the hardware and the probe, wedge, and materials, and some introduction to the beam formation. 1D linear array of probes are overwhelmingly the majority of what's used in convention or in portable small system phased array like the OmniScan MX2. You see here 4 examples of one-dimensional linear arrays. These have the elements all aligned in one axis. They allow focus only in one axis, and they can either be flat or curved. And in a curved internal focus like this, we're combining the beam steering from the phased array with the mechanical focus of the probes. The complexity of the software needed to generate focal laws or A scans from other probes can be very complex. So we use several different environments where we're weighing easy, fast, simple for 1D arrays against a more complicated computer-based calculator for other geometries. And again, in this first 4-part series, and the overwhelming majority of OmniScan work is being done with 1D linear arrays. So a 1D linear array is defined by the following parameters. What does the calculator or instrument need to drive this probe and give us what we want? The pitch or size of the element is known, and the majority of weld-type probes that we use have a pitch somewhere between about 1/2 millimeter to 1 millimeter. It's a very common. The probes come in common element categories designed for the instrumentation, which are typically 16, 32, and 64. The overwhelming majority of those. In large industrial systems, the instruments have the capability of managing up to a 128 or 256 element array. Frequency is exactly the same as conventional UT. It cannot be controlled by the software. It's a function of the hardware, and it's a compromise between penetration and sensitivity. Radius or flat probes can combine mechanical steering, and the calculator also needs to know a reference point. Inside this housing, the elements cannot be seen, so a reference in the entry is made from the edge of the internal housing. This allows a probe or a wedge to be programmed correctly. In the MX2 environment, on the instrument itself, all of the probe parameters are easily taken care of for the calculator because the probe has a chip that's automatically read by the software. The software needs to know the probe model, frequency, element quantity, the total number of elements in the probe, the size of those elements, a reference point, and it's a serial number is possible, but it has nothing to do with the focal law calculator. And in the instrument, and you'll see this in the upcoming lesson, with auto detect on, those parameters are automatically selected. With auto detect off, they're selected from a database or can be created. In a more complicated probe, outside of the instrument, it requires a more complicated focal law calculator. The reason I included this slide in an introductory class is to demonstrate the point that all calculators from all manufacturers are basically divided up into 4 groups. 3 parts hardware, 1 part software. If you give the software all of the correct information for the probe, the material, and the wedge, you can then ask for the beam information. Different calculators, different manufacturers have different levels of predictability for what's acceptable or not. But for the most part, we're dealing with the same physics as conventional UT. First and second critical angles, the ability for a incident angle to refract into the material, all of those things like Snell's law are very relevant. So we define the probe, or some common nomenclature associated with phased array related to the probe, is the aperture. The aperture is the total size of the probe. In terms of the beam aperture, it would be the conventional equivalent of the diameter or size of a conventional probe. The more elements we group together, the larger the aperture. The aperture is a term we will use. It's directly related also to the cost and versatility of the instrument modules. The element height, or also called the elevation, in this axis, the pitch of the probe is primarily what calculators will use to define the size, and it is a center-to-center spacing. Again, 0.6 millimeters, 1 millimeter is typically what we use for most weld inspections. The Olympus probes come with a housing family that makes compatibility between the different wedges easy. Any A1 probe can handle the wedges from the A1 family. In this case, we're looking at a very common weld inspection probe from the A2 family that comes in 2 different frequencies with 2 different size elements, resulting in a different aperture. The smaller the pitch of the probe, the easier it is to beam steer beyond the normal nominal Snell's law refracted angle. So the next series of slides are going to look at a number of different probes and what makes them unique for the application they're designed to be used. One of the most common families of probes is the A10, 11, 12, and 14. These are ergonomically designed to be used either in scanners or with the hand. They come into common weld frequencies between about 5 and 7 megahertz. They have different numbers of elements depending on the beam strategy and different size pitch. Very common weld probes. Probe designed for pipeline girth weld inspection is a little bit more specialized, would have a radial internal focus for improved length sizing, would be combined with Toft or other conventional probes as well, and would have a very specific job described in the phaser in the catalog. Pipeline probes. Deep penetration probes are much larger pitch, They have a much larger elevation or wider for penetration and lower frequency. Probes for small diameter tubing have a very small pitch of 0.25 or 0.3 millimeters. In this example, we'll see a small stainless steel piping tube with 2 radius curved probes that are designed for a very small clearance, up to 12 millimeter clearance. They fit on a small scanner, and they're optimized to get as close to the weld as possible with as small as footprint as possible. Again, specialized probes designed to be used in a specialized application, in this case, small diameter tubing. Probes for immersion tanks would be very similar construction, but would have an impedance matching value for water. They're still defined by frequency, number of elements, and pitch. They are typically much larger element count because they're used for coverage of composite aircraft inspection, large components. It's normally a speed or a race for the productivity as much as it is an improvement over the conventional inspections. Small manual crack sizing probes used in power generation or refinery in-service inspection. These are designed for crack sizing. They have an optimized small footprint wedge. They're very small. They have a lower frequency range because they're often used in stainless steels and spun cast stainless steels. And they're typical of the qualification examinations that would be required in the power gen or some of the refinery construction work, in-service work. And there's a number of specialized arrays for specialized applications that come in different shapes and sizes. All examples of 1D linear arrays. In this case, we're combining a mechanical beam steering or a mechanical steering and focusing with the phased array. In this case, we're designed for composite inspections for either the outside corner or inside corner for the composite panels, which make up a very large market for new phased array instrument sales. So that was just a little bit about the probes. I mentioned probes are one part of 3 for the hardware. The next set of hardware we need to discuss before actually programming the phased array are the wedges. The wedges perform the exact same function as conventional UT. They coupled energy from the probe to the material at the desired refracted angle and wave type. They come in all shapes and sizes. They can be customized. They're specialized in the catalog for scanners or manual inspection. They generally can be divided into 3 specific groups in our catalog and in the applications. Shear wave angle beam inspection. In this case, we would steer the beam at a refracted natural angle of 55 degrees in carbon steel, so we would cut this wedge at approximately 36 degrees. The smaller the pitch of the probe, the greater the beam steering below and above 55 degrees. In the longitudinal wave beam, like you see here, we cut the wedge at a much lower angle, 19 to 23 degrees. So it optimizes a natural 45 longitudinal wave inspection. Okay, often we get asked, can the same wedge generate shear and longitudinal? And the answer is yes, but the beam steering limitations for what's not optimized would be severely reduced. And then the other type, the third type, is the longitudinal straight beam. In this probe is designed mostly for coverage of what would normally done with a 0 degree inspection But we can also generate longitudinal angles and traditional sector scans from this wedge. Most everything we do that's not customized would fall into one of these three categories. Wedges, more than any other part of the equation, account for the overwhelming majority of our support issues and impede customers from doing what they're trying to do. Most of the wedge issues come directly from the calculator not knowing exactly what the parameters are that you're programming. A probe is in the wrong orientation. It's possible that this cable can come out of either side, and there's wedge entries in the database to account for that. Different models of housings have positions on different wedges, and it's very important that the calculator know exactly the orientation and size and parameters of the wedge. And in this case, an A2 family can go on a compatible wedge with slots for either position. The wedges are made of Rexolite. They're high quality machining. They have a very tight tolerance. Rexolite is extremely useful for phased array because it's a frequency retraining properties. It has a constant velocity in every axis. That's very important. For that reason, they tend to cost more than lucite wedges. Any flaw in the wedge or the dampening material is susceptible to much more wedge noise and interference than in a conventional UT. And again, our nominal 60-degree shear wave designed for the SA1 housing, these are the scanner options for water ports or mechanical feet that prevent the wedge wear on an automated scanner, and then the orientation or the cut of the wedge. Excuse me. In this case, a 39-degree shear wave wedge incident angle relates to the refracted angle in the carbon steel for the shear wave. Most of these wedges are designed for about a 30 to 70-degree sector scan that can be calibrated on normal side drilled holes and notches. Wedges also include accessories and water ports, or the ability in this case to stand flat on a pipe without a curved, without a radius wedge. 0-degree inspection we're looking at here, that would be a corrosion map, one-line scan. The footprint inside the wedge would be about 50 millimeters, and inside that 50 millimeters we have an individual A-scan for every focal law or group of elements. All of those together can collect a C-scan. The S-scan you see here is made up of many individual A-scans. The blue cursor, as I move it from side to side, shows me the same A-scan that it represents. So the wedges are also designed to come in different orientations and different cuts or curvatures. Most of them that we use are flat wedges on pipes and vessels in this orientation, but for the automated scanning, the scanners require an axial or circumferential curvature seen here, and they're ordered with the appropriate curvature from the catalog. Some of these require special consideration in the calculator. Some of them, like the axial outside diameter that you see here, are designed so the height of the elements are the same as flat, and it's not a consideration. The wedges in the circumferential orientation, like you see here, or a COD wedge, require a calculator to be imported into the MX2, as the onboard calculator doesn't have that capability. And we'll see examples of all of these when we start programming the phased array. Wedges can also be a water wedge, like you see here. We have a 0-degree probe, and the probe is adjustable for a different water column height and has a foam seal and water ports inside and outside so that it retains the water. We remove the bubbles with a little bleed system, and this effectively gives us a little portable immersion tank. The benefits of a water wedge are very good near surface resolution, my ability to detect flaws near the surface. It also allows us to walk or move the scanner over a contoured or rough surface, and as long as the water is retained, the signal is very good. And it allows us a feature often used in immersion tanks called a floating gate and echo synchronization on the A-scan, meaning that I can set a gate over the interface signal, and my other positions for backwall 1 and 2 become floating gates. And it gives us a lot of immersion tank functionality in a small portable system. The wedges are also designed to be custom made. In this case, the wedge was machined to meet the same contour as the component. Looking across the component, we can see both a position C-scan for where we see wear or erosion or metal loss, and an amplitude-based C-scan. Both useful tools we'll learn more about when we get to the applications portion. So, what does the OmniScan need to know about the wedge, similarly to what it needed as the probe? The probe was automatically detected and populated from a chip. That's not possible with the wedge. So that information must be pulled either from a database, preferably, or entered manually from a wedge that's been modified or purchased from some other manufacturer. So the software, upon selection of the wedge model and probe from the database, needs to know the angle, in this case 0, needs to know the orientation. This would be a design so that we could reverse the probe from elements 1 to 64 to elements 1 to 64. We can flip-flop the probe. The velocity is a constant for Rexolite. The height of this first element in the wedge is very important for the software to be able to do the beam formation. The reference is very important for displaying data. It has nothing to do with the beam formation, but when the software knows that the position of element number 1 here is minus 56 millimeters from the edge of the wedge, the software can return data with the rulers and cursors in the correct position. So on any given probe and wedge, the orientation of the elements on the wedge must be known. Different manufacturers use different schemes to come up with that, but some common ones are the position of element 1 here, defined as the height here. The angle of the wedge, again, for shear wave or longitudinal, is defined. Those directly affect the beam formation and beam steering. There are also offset or position information, if known, so that the C scans and B scans and D scans display the data in relationship to the weld or the component correctly. All wedges purchased come with a printout of the actual information needed to program them. Regardless of what the calculator you're using, whether it's the onboard OmniScan, the setup builder, or TomoView, the information you need is provided in a spec sheet for the wedge. Some of this information can be measured acoustically or mechanically if it's not known. Obviously, the safest, easiest way is to select it from the database. So that was 2 of our 3 hardware parts: probe, wedge, material. So when we talk about material, the third part, we're really talking about only velocity. The thickness of the material, the width, the weld bevel, all of those things can be modified after beam formation or after acquisition and reverse engineered in the data if necessary. But what cannot be changed, what has to be known when the focal laws are formed, is the velocity. When you recalibrate velocity in the OmniScan, you're actually rebuilding the focal laws. And this is true for all software. It's just a physics thing more than a software limitation. So you must know the velocity. Normally, for carbon steel weld inspection using normal P numbers and typical API piping, selection of the velocity from the database is just as accurate as your ability to measure it for the delta. There are several ways of measuring velocity. We'll talk about those in later sections. Normally, it's selected from the database. We want you to understand that when you calibrate velocity, if your error rate delta for measuring it is greater than the angular error created by using the database, you're creating work unnecessarily. And we'll talk a little bit more about that upcoming as well. But the important point for the component is the material velocity is what we need to know about it. So before we move on to beamforming, we're going to take another look at the inspection up to this point. We talked about the probe and what we need to know about it, number of elements, pitch of the elements, and size and frequency of the elements. We talked about the wedge, height of the first element, angle of the wedge, velocity of the material, Rexolite in this case, for the beam steering. To be able to visualize this hole at the correct position, the software also needs to know the reference of everything in relationship to the front of the wedge. In most of our applications, the user or the operator is going to manage everything from the face of the wedge, and the software is going to manage everything, including all of the exit points inside the wedge. If the material velocity of this calibration block was entered correctly, then the beam formation with those parameters is going to give me what I need to form the correct angle at the correct position. And my ability to be able to place the depth and the location away from the probe face correctly, 34 millimeters in front of the wedge face and half an inch or 12 millimeters below the surface is where we'll see the calibration, reflector, or the defect. So those are very important. When those parameters are entered correctly, right away, my ability, looking at the S-scan, when I'm looking at the calibration target across all of the angles, in this case at 45 degrees, all the way over to 70 degrees. If it is flat and at the correct expected depth, it is an immediate indication that the probe, the wedge, the velocity of the wedge and the velocity of the material were all entered into the calculator correctly. There are several functions for calibration. Nothing is more accurate than giving the calculator the correct information from the very beginning. Here we see the OmniPC environment, and we could look at that same basic information from a more complicated calculator that we see here in TomoView. Probe, material, and we'll see more information than just material velocity for higher functions used in other software. Wedge identified. Once the hardware is all entered, I can start asking for beam information that will change the size, shape, focus, and angle of all of the focal laws. So one of our environments in doing that is directly on the instrument. Another environment for us doing those same things is the NDT SUB setup builder. So to recap, probe, wedge, material. Under the menu, the first thing we'll do is select the instrument that we're using. This is important because the pulsar element configuration and the total element configuration, if known by the software, will not allow us to create a setup that's not compatible with the instrument we're using. So when we look at the probe, we'll see a database full of different probes, the part, not the probe. We have a velocity for longitudinal and shear wave. We can select from plate, tube, or bar. We can enter the thickness, the length, select any number of welds, and generate the weld bevel. But for the beam formation, all it needed to know was the actual velocity. Under the probe tab, we have similar information as the OmniScan database, and we can manage this directly here. Probes are added or removed, can be cloned and copied in reverse position directly on the interface. So this is a linear PA probe. TOP and UT probes are also programmable. From the A2 family, it's the 5L64. The model number is entered here. It's in a position of skew 90. So depending on the orientation relative to the weld, we define it, and we define its position in or out from the weld. The wedges, the same family of wedges associated with the probe. So those are very quickly and easily plotted on our beam simulation or plotter tool called the NDT SUB. Probe, wedge, material. In the OmniScan instrument itself, which we're looking at now, and this is of the different environments we're going to be working on during the training, the instrument live captured through video over the internet will probably be the slowest or maybe the worst quality. So bear with me. I'll try to navigate slowly and move directly to. But in the instrument environment, using the wizards, our setup wizard and part weld wizard will recreate the same environments for a simple 1D linear array probe that we just discussed in the computer-based version of that. It's an onboard calculator that will allow us to walk through this several steps at a time, asking us for the component information, the weld information, and then continuing on to the setup of the probe, wedge, and beam formation. Coming back to our presentation. Now we're getting into the beam formation portion of the presentation, the most important part. We've configured our probe, wedge, and material. So what exactly happens to form this one A-scan with a multi-element phased array probe? This is also called a focal law. It's a time delay applied to the pulsing and receiving elements of a probe in order to steer and focus the resulting sound beam and echo response. Many of these combined together make up the group, but any one A-scan is defined as the focal law. In a pulse echo inspection, meaning a single element is used to transmit and that same element is used to receive, the focal law is exactly the same as the transmitter and receiver. There's a set of delays from elements 1 through 16 for the transmit and for the receive. The more elements you have in the probe or the instrument capability, the longer your focus is capable of achieving and the more powerful the instrumentation. So when each element is excited in a focal law, we can see that there's an individual wave front associated with that one element, but the sum of all of the waves together, or individual A-scans, are summed into a focal law that gives us basically the equivalent of what we're already used to seeing in conventional UT. The same properties for Snell's law or the physics of refracted and incident angles still apply. All of what you learned in your level 1 UT class is still applicable. The only difference is how we're generating the A-scan. And those come in basically two different groups of inspection strategies, or scans they call them. There's many forms of these, but the two most common and the two that are supported directly in the OmniScan calculator are a sector scan group and a linear scan group. So a sector scan group is going to fire all of the A-scans or focal laws from one group of elements. They will have a different exit point because of the angle is slightly different. But for the most part, it's one group of elements forming the 45, the 46, the 47, the 48. This allows a cheaper and instrument with fewer elements to be used in phased array inspection. It also generates the pie-shaped display that most people are normally associated with. There are advantages and disadvantages regarding calibration, ability to conform with conventional existing procedures and codes. Then there's the linear scan. The linear scan is going to take the same angle. In this case, I think it's about a 50-degree angle, and it's going to step that 50-degree angle through the entire probe. Element 1 through 16 for focal law 1, element 49 through 64 for focal law last. The benefit of the linear scan is it uses one angle and is effectively the exact same thing as a conventional raster scan. We're replacing the mechanical movement of a two-axis scanner with an electrical raster for every A-scan has the same functionality. Our beam formation is also affected by our ability to focus. This is relative to the near field that we'll explain shortly, but it's mostly affected by the number of elements available in the instrument, the number of elements available in the probe, and the number of elements we program in the probe for the beam. More elements result in more steering ability and better focusing. We'll see many examples of this when we get into the data analysis and different focus strategies. So if we were to pull out our calculator, which in phased array we don't necessarily need in our day-to-day business, but any given probe's aperture, the number of elements being used times the size of those elements and the frequency, you can arrive at the theoretical near field calculation. Okay, the near field distance is the maximum distance theoretically from which beam convergence or focusing can happen. In many of our applications, like ASME weld inspection of new construction, the reject rate is designed to be used for compared to side drilled holes or notches in calibration samples. To have a phased array inspection generate the same reject rate, you would need to use an unfocused probe by entering a number larger than the near field. Different focus strategies can be in depth focus plane, a sound path focus plane, projection focus plane, or a focus plane designed by an XY position in the material. Only the OmniScan can generate the depth. In the OmniScan, only the depth focus is available. In the external calculators, we have the ability to use different focus strategies by importing directly into the instrument from the flashcard. When we use standard calibration blocks, designed both for conventional UT and phased array, any given probe aperture, size, shape, wedge, with a beam focus and angular resolution, we can look on standard calibration blocks and determine the useful working range of what any given probe and wedge is capable of. The calculators would allow me to program a 20-degree beam. But if I looked at the A-scan quality of a 20-degree shear wave, it would be unusable. So, in other words, experimentation on cal blocks, more so than computers trying to predict what's acceptable to one customer or not, is how we determine and verify the useful range of what we're claiming. And of the three focus strategies that you see here for depth, sound, and projection, looking at a cal block like this for half path, projection, or depth shows you the advantage to focusing, where all of these would be very clear under the focus strategy it's designed for. They would be very unclear otherwise. So we're going to go back to the desktop environment and talk a little bit about what we've covered up to this point for the beam steering. Okay, so we're back into the NDT setup builder, which is what we use to plot. After we have configured the component, the probe, and the wedge, primarily from database entries, now we can move to the beam formation. A group defined in the OmniScan is a group of focal laws, or A-scans, that share a common skew and channel within the instrument. So if we were to look at a single group that includes one static A-scan here, to put in play some of the terminology that we talked about, the single A-scan here is being developed from our phased array probe 1. We are asking for a shear wave velocity refracted angle in the material of 55 degrees. I can change that angle directly in the calculator. Okay, this one A-scan starts on element number 30 right here, element 30, and uses 16 total elements. So 16 elements times the pitch of each element, 0.6, equals 9.6 millimeters. So my aperture here is of basically a 10 millimeter probe. Okay? I'm limited in my configuration now. I cannot type in a larger number than 16. Were I using an acquisition unit with more capacity, then I would have the ability to use more elements. So I have a focus distance here of 50 millimeters in true depth. One static focal law group. Another type of group we use is called the sector scan group. And this is the most common type of group most people associate with phased array. In the sector scan group, again, we're going to use the same group of elements as our static focal law, all starting on element number 30 here. If I were to move that to element 1, I'm further away from the weld. So I can either move the probe closer to the weld, or from my normal inspection position, I can move the aperture inside to an appropriate position. Okay, the sector scan that you see here is the exact sector scan you see here, from 45 to 70 degree, and this is a calibrated inspection of this calibration block. 1.5 millimeter side drilled holes in a typical nav ship or similar type configuration. And as we see, calibrated correctly, any side drilled hole is at 80% amplitude and at the correct position. If I were to drive the scanner, we can also see that any one A-scan would also have a similar, or in fact, exactly the same TCG and calibration, and this is visualized in the color palette. We're going to talk about displays later, but in all of this, we're converting color to amplitude or color to position. It allows us to visualize many things at one time, including many A-scans, many angles. But it all comes back to this same A-scan. So in our sector scan, we want to find the position of the probe and position the aperture appropriately in the probe so that we can cover our component. Another type of group is the linear scan group. In this case, we select linear here, and it's all going to be at one angle, 60 degree. A perfect inspection for a 30-degree weld bevel is a 60-degree incident angle. So we're simply replacing mechanical movement with electrical movement of the beam. This is defined as the element start position, element 1, for the first A-scan. I want to use the entire probe, so I will stop at the last element. Okay, I might not need all of that coverage, but I have the ability to use it up until the last 16 elements. So the size of each of those A-scans or beams is the conventional equivalent of a 5 megahertz, 10 millimeter conventional UT probe, but I have an A-scan every 0.6 millimeters across the entire array. In this environment, I can directly export the connectivity file to a group in the MX2 instrument. So it saves me the time of using the onboard calculator of the instrument for multi-group configuration. So we've come to the end of our first lesson, which is an introduction to the phased array with a focus on the equipment we use. Our next presentation is going to get into instrumentation and examples of actually forming the beam and using the instrument online live and how we develop those A-scans. There were a lot of questions throughout the course of this, so we're running a little short on time. They'll all be answered in an email that you'll all receive with a link to the archived video and this presentation as well. So I'm going to turn this back over to our moderator, Greg. I want to thank you all for participating and look forward to you guys coming back next time. Greg, take it away.
Thanks, Chris. On behalf of Olympus NDT, I'd like to thank Chris Magruder for his participation in today's event. Thanks very much to all the attendees for joining us. We hope the material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com shortly after the presentation is done here. And it will be archived along with all the Q&A questions along with it. If you have specific questions needed to be answered about anything that you heard today, please send an email to the address that you see on the screen, phasedarraysupport@olympusndt.com. And that's going to do it for today. And again, thanks to everyone for participating. We'll see you again next time.